Moles are like the connection basically between mass and the number of the mass of a substance and the number of atoms or molecules in a substance. All right. So we're going to talk about moles and how that connects the two concepts of the macro and the micro realms. We're going to talk about empirical formulas and molecular formulas. And then molarity. And the connection between all of these things is the mole, right? The moles, molarity just expresses moles as it relates to solutions as opposed to solids. So molarity, and then we're going to talk about solutions, and this is always, molarity is always expressed as moles per liter, right? So where we talk about moles, normally we're talking about a solid substance, but then we also can determine the number of moles in a solution using molarity. So with that being said, we're going to jump right in and hit this first topic, which is formula mass. And this is a pretty uh, mild topic to deal with because, again, if you know your way even a little bit around the periodic table, then you'll be able to figure this one out with no problem. But it's just a matter of having the experience of, looking at the periodic table and figuring out what the atomic masses are for specific compounds. So we know we're able to do that. We've done that already, right? So when we talk about picking this pencil up a little bit, formula mass, all that is the total right, the total atomic mass for a compound. You literally determine the formula mass by summing up every atom. Right, so it's the sum of atomic masses for all atoms in a particular compound. And this morning, we talked about quite a few compounds, and we're going to do that here also. But again, you'll see formula mass sometimes called molar mass. I think I left that out in the outline. You'll see it called sometimes molecular weight. It's all interchangeable. All means the same thing. It's the sum of all atoms, the atomic masses for all atoms in a compound. And you can express this in AMU, which we're going to do initially, but you can also express it using another unit called grams per mole. Right, so AMU, grams per mole. We're gonna start out with AMU simply because that's what we're used to up to this point. We haven't discussed how grams per mole actually works or how we're able to get to that expression, but we will talk about that shortly. So we're going to start out in AMU. So the first compound we're going to look at is ibuprofen. And I'm going to sure I got the right structure here. All right, so somebody look up the molecular formula for ibuprofen. sure that I think that's the right structure. We'll make sure there's not another carbon where that acid is. And there is the 2 carbons. Yep. All right, we got it now. All right. So this is ibuprofen. Right. You probably have taken ibuprofen at some point in your life, especially if you have like an allergy to acetaminophen or aspirin or naproxen. Uh, right. You've probably taken this for a headache, for inflammation, swelling, whatever. All right. So everywhere, did somebody look the formula up yet for ibuprofen? I'm gonna explain the structure too and all that. Uh, Anybody got it yet? The molecular formula for ibuprofen. You can see that it's going to basically
Is it hold on one second. C13H18O2.
yes, I see 2 people in the chat with it too. Thank you. C13H18O2. Now let me explain how this matches the structure that's shown, and then we're going to go back and we're going to talk about uh, the atomic masses and what we have to do in order to determine how much of each one of those atoms is present in this molecule. So everywhere you see a vertex, let me use a different color. That's too light. Everywhere you see a vertex, so here, 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 these are all carbons. All right. In addition to the carbons that you see right here, like this carbon, and this carbon. Right. So this is what we call a skeletal form. You'll learn more about this when we get to when you get to organic 1. And what I've noticed is because I teach organic 1 and organic 2, what I've noticed is that a lot of times when I get students in organic 1, they don't have the foundational, like the rudimentary part about structures. But we're going to learn that. We can do Lewis structures, which we'll do later, but we also need to learn a couple of the other ways to express these things. So this is what's called a skeletal form. And if you notice, the carbons here are, we can number them 1, not in any order, 4, 5, 6, 7, 8, 9, 10, 11, 12. I'm missing a carbon somewhere. Right here, 13. All right, there's no order, so don't worry about that. But we got 13. You can see that there are 13 carbons. And then for the hydrogens, you can see that there is 1 hydrogen here. There are 3 here. There are 3 here. And there are 3 here. And actually, let me go a step further and draw those out so you can see exactly what this thing looks like. This first. Right, so when you see the CH3s, let me show you what that actually looks like. So that carbon actually has 3 hydrogens bonded to it covalently. All this is all covalent, nothing ionic, like that. And then this carbon over here is going to look the same way. Right, just as a kind of a rule of thumb for later, all carbons make 4 bonds, 4 covalent bonds. That's just the valence of carbon and allows it to make 4 covalent bonds. So anytime you see a carbon sticking off somewhere like that, it's unless there's another atom attached, it's a CH3. All right, so now let's count up the hydrogen. So here, let me just switch colors right quick. Well, no, I was using purple. So here, that's 3. That's 3. That's 3. right there. And then there's also one here that you can't see, but I'm gonna show it. Right. So how many hydrogens is that? Does that match up? We got 18. We got hydrogens here. They're really everywhere, but we don't want to get jammed up by not showing them. And here, here, and here. All these are hydrogens. For the most part, on a skeletal form, if a position doesn't have anything on it, like you don't see anything, it's assumed that there's a hydrogen there. All right, so let's count these up. How many hydrogens is that? Let's make sure we got the right amount. So that's 1, that's 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. I'm missing one somewhere. Here. There's also one there. So that's 18 hydrogens. And then obviously you can see the 2 oxygens, right? Here and here. So that's why ibuprofen has this molecular formula of C13H18O2. So now when it comes to calculating the formula mass, right, what we need are the atomic masses of each atom. That's it. So for carbon, atomic mass is 12.01 AMU. And because there are 13 carbons in that structure, we're going to multiply that by 13. For hydrogen, it is 1.008 AMU times 18. And then for oxygen, it is 15.99 AMU times 2. Everybody following that? Anybody not following? Feel free to interrupt or ask a question. All right, and this is the same. You'll do the same for any molecule, any compound, whether it's covalent or ionic. You're going to do the same thing. You're going to find out how many atoms are present of each, how many of each atom is present, and multiply that number by the atomic mass for that atom. And that's how you, and then after you do that, we'll sum all of it up. And that will be the formula weight. So it's the sum of all of these numbers. So 12 times 13, what do we got there? 156 point something. Anybody calculated that yet? All right, so 12.01. It's going to be 156.13. Somebody calculate the oxygen one. And this is an AMU. Right? And then for hydrogen, be that times 18, 18.14. And then anybody got the oxygen one yet?
$31.98.
31.98. And this is all in AMU as the unit. All right. So the sum of those 3 numbers is going to give me my formula weight, or formula mass, or molecular weight, or molar mass. It's all those terms are interchangeable. So 156.13 plus 18.14 0.14 plus 31.98. What do you got? So it's 206.25 AMU. All right. We can also express that again in grams per mole, which we're going to talk about shortly. All right. So for ibuprofen, it has a formula weight or molecular weight of 206.25 AMU. All right. Questions about that one? All right. Let's do a second one. Let's do pentane. Actually, let's switch this up. Let's do pentane. Pentane is going to be C5H12, right? I think in the earlier section I put pentane, but I drew out propane. All right. So this is going to be 5 carbons like this. All of them are it's a saturated compound. In organic, we call this type of compound an alkane. Right? It's all carbon, hydrogen, single bonds. So you can see it's C5. So 5 carbons, and then you can also count up the hydrogens. So that's 3 there. That's 3 there. That makes 6, and then 6 there. So for a total of 12 hydrogens. All right. So when we calculate the formula weight for this, it is what? Carbon, which is 12.01 times 5, and then hydrogen, which is 1.008 times 12. Somebody give me that. Give me those two numbers real quick.
The first one is 60.05.
0.05. Okay, and this is again in AMU. And then what about the second one?
12.096.
All right, and then you add those two together, you get what? 72.146. Is that right? So 72.14, and we can round that up, 72.15 AMU. Right, so this is again formula mass, molecular weight, molar mass, however you want, or formula weight, however you want to call it. Right, it's the same when you have ionic compounds. It doesn't change from covalent to ionic, and there's a reason for that. All right, somebody tell me. Let me first. Since we just took an exam on this, let me see what you got. What's the name of this compound?
Is it aluminum oxide?
Excellent, aluminum oxide. I know I heard somebody else about to chime in too. Were you gonna say the same thing?
Yes.
All right, cool. Aluminum oxide. And in order to get the formula mass or the molecular weight or molar mass of this, what do I need to do? I need the atomic mass of aluminum and the atomic mass of oxygen, which we've already done multiple times. So this is 15.99, and then aluminum is what? Anybody look at the periodic table real quick and tell me what the atomic mass is.
26.98.
6.98. And then there are 2 aluminums in this formula. So we're gonna make sure we take note of that and multiply that by 2. And then there are 3 here. So we need to make sure that we multiply this by 3. And then we're gonna take the sum. All right, so 26.98 times 2. What do we have from that?
53.96.
All right, 53.96, and then 15.99 times 3 should be 47 and some change. Is that right?
Yes, sir. 47.97.
All right, cool. So sum those up, and then that's the molecular weight for aluminum oxide. And this is again all in AMU. All right, let's do one more because this morning I screwed this example up. Well, it wasn't that like a crazy screw up, but it was what it was. I'm human. So let's take this compound, and I want to see how you're thinking about this. What's the name of this compound? Anybody?
Calcium phosphate.
Excellent. That's calcium phosphate. And one of the things, let me say this about ionic compounds like these. How does an atom become an ion?
By losing or gaining electrons.
Losing or gaining, great. Losing or gaining electrons. If you notice, we haven't taken any new approach with these ionic compounds. It's the exact same approach. And that's because the mass of an electron is like 1,000 times less than the mass of a proton or a neutron. So it does not contribute as much to the atomic, the overall atomic mass of an atom. So we don't care if we lost an electron or we gained an electron. The ions have relatively the same atomic mass as the atom itself in its neutral state. So we're not taking into account, because these are ionic compounds, we're not taking the mass of electrons into account at all, because they're so small compared to what gives the atom its mass that it doesn't matter. All right. So here we have calcium, and this is what's the atomic mass for calcium on the periodic table? Anybody got it?
$40.07.
40.07 AMU, and then we got 3 of them over here. All right, so we're going to multiply that by 3. I'll slide all this over to make room. What about phosphorus? What about phosphorus? What do you think?
30.97.
30.97. How many of them do we have?
4.
Let's see. All right, so we got 4
Yeah.
oxygens here. But we also have outside the parentheses, and see, this is why knowing those charges is so important, because if we pull this apart, like looking at it from the crisscross method, so this is Ca2 plus, and then PO4 minus 3, right? But that 2 out there, when we crisscross it, it has to get distributed to both the oxygen and the phosphorus. So we actually got 2 phosphorus atoms here. And then for oxygen, which is again 15.99, we have 8. Do you see that? Anybody not seeing that? So that little subscript matters, right? It might seem insignificant when we're naming, but that substrate is not just there for the name, it's also there to give an account for how many atoms are present, right? And depending on the charges on the ions, that's going to determine the substrates, because you just crisscross them up to get the charges. So let's knock these calculations out real quick. We're gonna do one more of these, and then we're gonna start talking about moles. All right, so somebody got, what's that? 120.21 for calcium.
Yes, sir.
120.21 AMU. And then for phosphorus, it's going to be 61.94. Is that right?
Yes, sir.
AMU. And for oxygen, 15.99 times 8. Somebody give me that number real quick.
127.92.
127.92 AMU. So we're going to sum those up, and that'll give us our formula mass or formula weight for calcium phosphate. And all of these numbers, you can Google them and see how close we are. They may be a little off on the decimals, simply because sometimes with the atomic mass, you can go out several decimal places. And some of the calculations are more precise, so they use more decimal places. But for this, we're good. If we get even within 0.1%, we're good. So I'm not really tripping about that. I'd much rather you understand the process, because you can you can just use the numbers from the periodic table to figure out the atomic masses. The periodic table that's given, like if you're given a periodic table on the exam. Go ahead. Anybody got it?
310.07.
10.07, and this is in AMU. All right. So that's the atomic, the formula weight, or the molar mass, or the molecular weight for calcium phosphate. This is very important, a very important concept to understand, because when we're doing lab, and especially when we get to like the the limited reactant lab and all of that, all of those labs like that, they rely heavily on you being able to calculate the molar mass of a given compound. All right. Any questions so far? Everybody still on the boat?
Yes, sir.
All right. So now we're going to move into, and I'm going to leave one for you. I'll leave you a breadcrumb. So name and formula weight. You can work on that at some point. I think also, let me say this while I'm thinking about it. I think Wednesday is supposed to be a mental health day. I think that's what's scheduled. So we won't meet on Wednesday. What we'll do is on Thursday, which is our recitation day, we'll just keep pushing with this, and then I'll have some examples that we'll work through. But yeah, some of the professors are kind of in an uproar about Wednesday, because I think they moved it. It was supposed to be Thursday, but I think they moved it to Wednesday, because Thursday is midterm. So I don't know. Anyway, whatever happens, we're gonna take the mental health day, whether it's Wednesday or Thursday, it doesn't matter. But right now, it's still Wednesday. All right. So now, now let's go ahead and switch. Switch gears, and we're gonna talk about the mole and what it is. Right. So when you have a particular compound and you want to identify it, what identifies any compound, there are two key factors: the atoms and the number of each type of atoms. Those two things identify any given compound. Right, or any substance. All right. So you think about, and I did this morning, and I'll do it again here. right? This is water. This is hydrogen peroxide. Notice how they're made up of the same basic atoms, hydrogen and oxygen, but the ratios are different, right? H2O2 versus H2O1. Remember that if there's nothing here, it's understood to be one, right? And I'm sure
I
that
have a
Go ahead.
question.
Go right ahead.
Why is it called hydrogen peroxide and not just hydrogen oxide?
Good question. Good question. So hydrogen peroxide, a peroxide, and this is the structure of it. It usually has one extra oxygen in it. And so like water is like this, H-O-H. See how it has one oxygen? So this is really dihydrogen oxide. Right? So this is the oxide, but if you notice, hydrogen peroxide is like an analog of water. And so because it has that extra oxygen here, that makes it a peroxide because it has one extra oxygen in it. That's what the per prefix actually indicates in this case, is that you have one extra oxygen in your structure. And since this is an analog of water, that's why it's called peroxide. That's a great question. Does that answer it though? Or does that make sense to you?
Yes, sir. Thank you.
Mm-hmm. They have the same atoms, but they have them in different ratios and different amounts. So they're two different compounds. So the way that we measure atoms and molecules and compounds is we measure them in moles. So I use to measure atoms, molecules, compounds, and the mole is actually it'll tell you like the exact number. It can tell you the exact number of atoms or molecules in a bulk sample. Right. So what the mole is a bridge. It's a bridge between the macro and the micro, right? So moles is a bridge between the macro realm, which is the mass, and the micro realm, which are the atoms or the ions or molecules that make up the substance that has mass, or that particular matter that we're taking the mass of. So it's a bridge between macro and micro. So bulk mass and then micro. Right. So the atoms or ions or molecules that make up the sample of a substance is measured with moles, and then it also helps us to navigate between the mass of the substance itself, which is typically going to be in grams, right? Not the weight. We talked about that way back in chapter 1. There's a difference between mass and weight. And so the way we navigate between the macro and the micro is the use of moles. But there's another number that's really important to going between these two realms. And that is, you probably heard this in your high school chemistry class, and that is Avogadro's number, right? Which is represented by uppercase N with a subscripted uppercase A, right? And what Avogadro's number allows us to do is figure out the micro part, because it is the number of discrete particles per mole. So the discrete particles are here. Let me put this a little tag out here. Because when you hear that phrase again, you'll know what it means. So the micro level, these are what we call discrete particles. And it can be an atom or a molecule or an ion, it doesn't matter. They're all considered discrete particles. All right, so Avogadro's number tells us the number of discrete particles per 1 mole. Right, so 1 mole of a substance has a specific number of discrete particles that is made of. Depending on what particle you are looking for, that's the particle that you'll put up top. So this can be, again, atoms, ions, or molecules, right? It's all interchangeable. It doesn't matter what you put there. But the number itself is 6.022 times 10 to the 23rd particles. That's in the top. This is the unit per mole, right? So it's always per mole. So any particle that you're looking for that a particular substance is composed of, you could put it in the top. Atoms, ions, molecules, hamburgers per mole, whatever. Basketballs per mole, footballs per mole. You can interchange this top number, right? That's interchangeable. Right, depending on the particle that you're looking for. All right. So as far as how Avogadro's number and how it relates to the number of discrete particles in a given number of moles, it's a simple calculation, right? If you know the number of moles, then you can multiply that by Avogadro's number. Let's say atoms per mole, right? And you can, of course, the moles will cancel and you're left with a certain number of atoms that are present. All right. So we're actually going to pause here and we're going to pick this up on Wednesday or Thursday. I'm not sure which day. I'll let them argue and fight about what day we're supposed to have this mental health day. And then once I find out the right information, then I'll send you an announcement and let you know which day we're going to take off. All right. Any questions about anything we talked about so far?